Alright, welcome back, everyone. So today we're going to be continuing our uh, section on span and linear independence, and we're taking the spot where we left off. Namely, we are looking at the definitions of linear independence and linear dependence. That is, linear independent sets of vectors and linear dependent sets of vectors. And so, why don't we quickly prove a proposition about, or theorem about linear independence, and that's going to be an equivalence statement. That is that a set of vectors, or we're going to start using set notation, that's better. Subspace of a vector space, V. Sorry, it's not a subspace, it's just a subset. This doesn't necessarily, that's an important remark, it doesn't necessarily have to be a subspace. And also, before we get to that, there are two important conventions that we left off from yesterday. Well, I forgot to mention yesterday. That is that, well, by definition, this is part of the definition of span. By definition, the set with just 0 is equal to the span of the empty set. And also, we say that the empty set is by definition linearly dependent. So those are the two conventions. Right, they don't really have much mathematical rigor behind them. They're just conventions that we have, right? Okay, so we have this list of vectors, subset of vectors in our vector space V. It's linearly independent. Again, I'm using abbreviations. If and only if none of the vectors are a linear combination of the others. Alright. And in fact, you can negate, if we prove this, you can negate the statement, and then that would, proving this would imply that the opposite holds true for linearly dependent sets. That is that at least one vector is a linear combination of the others. So we don't have to worry about that proof. I'll try to make this quick so that we have room for the other, for the more important proofs. Okay, well, let's see. For the first direction, light it up. All right, first direction. We're actually going to prove the contrapositive. So contrapositive, that is, suppose that vector, suppose that at least one vector is a linear combination of others. Call that one, let's call that one Vj. Well, actually, without loss of generality, let that vector, call that vector V1. It's without loss of generality because it really doesn't matter which vector we choose, it's just change in notation. So we write A1 at V1 as A1 A2 V2 plus ... AN Vn. Okay. Well, in that case, we can just subtract V1 on both sides. So we'll have, that implies that 0 equals minus 1 times V1 plus ... what we have here. But notice that this is a linear combination of these n vectors. But notice that at least one of these is non-zero because we have a -1 there. as a coefficient of v1, and so that contradicts the fact that, and so, well, we didn't go with contradiction, but we were proving contrapositive, that is that this, not this, implies not that. So we've proved that the set of n vectors is then linearly dependent, so that's a check mark by our definition here. Okay. Next direction, other direction. Hopefully we don't run out of ink here. So for this direction, let's see. We suppose that none of the vectors are linear combinations of the others. Then we want to show that it's linearly independent. Okay. Well, let's see. If we can still prove the contrapositive here, right? Or let's go with a different technique. Let's go with contradiction. By way of contradiction, just for fun, they're pretty much equivalent techniques, but by way of contradiction, suppose a set of vectors is linearly dependent, then it has to hold that there exists let's call it again, then without loss of generality, say v1 is non-zero, and so, for example, let's say v1 is non-zero, then a1 plus dot 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 an vn is equal to 0. There could be other vectors that are non-zero, but without loss of generality, we assume v1 is one of them. Then divide both sides by a1, which we assumed is non-zero, right? Divided by negative a1, in fact. So that implies, and then add v1 on both sides. And so, in general, we get that v1 is equal to negative, right, the negative, we'll distribute the negative sign, a2 over a1 v2 plus dot minus dot 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 minus an over a1 vn. These are still numbers inside our field vf, and so this is indeed a valid linear combination, and so we've written one of the vectors as a linear combination of the others, and so that is our desired contradiction, since we assume that none of the vectors are linear combinations of the others. So QED for that. Okay, so that's our easy theorem out of the way. Now let's get to the more interesting stuff. I think we can easily get rid of this definition. Keep those conventions in mind, though. Those will prove useful later, or at least one of those will prove useful. So now let's get to the linear independence lemma. Linear independence. Completely butchered that spelling. Lemma. Okay. Linear dependence lemma, sorry. Right, it should be, yeah, linear dependence lemma. Okay. So this has two parts. Again, suppose that the set of vectors all the way to Vn, subset of our vector space B is linearly dependent. Then there exists J, member of the set 1 all the way to n, so this natural number, set 1 to n, such that there exists J, such that the following two conditions hold. Well, for one, this Vj can be written as the span Vj is in, so it can be written as a linear combination of the others, but in other words, it is a member of the span of the previous vectors. So this is a bit different, but the proof is pretty much analogous. The span of the previous vectors, okay? And also that the span of, well, we can word this more efficiently, perhaps. Let's see. Yeah, he does it in words, but we can write it like this. The span of V1 through, we keep Vj, right, all the way to Vn is equal to the span. So the span is unchanged if we remove J. V1, kind of, yeah, badly written. We could write J minus 1, Vj plus 1, ... Vn. So this is not much more concise, but yeah, get the idea. So let's write out the proof. This is a lemma, so it's more of a technical result, not a particularly enlightening one. It's not a beautiful result, but we must prove it nonetheless because it's helpful to prove other more important theorems, such as the one that's coming up, the ones that are coming up. Okay, so proof. So first of all, let's prove the first thing, and then the second thing. First thing, well, it's analogous to the second direction in our first proof today. We take the largest J in the set. I wrote that badly, it's fine. Such that the Vj is non-zero. Okay? One must exist because it's a linearly dependent set, right? So we're taking the largest one there. And now, well, by definition, there exists A1, V1, ... and Vn such that this equals 0. And then all we have to do, divide both sides, somewhere Vj exists somewhere in there, divide by Aj. We should write Aj. Divide by Aj on both sides, okay? And then negative Aj, same process, add Vj on both sides, and essentially we've essentially let's see. Well, what we can do is we can just, what's different here is that we can just take an since it's the largest constant in the linear combination here, such that Aj is non-zero, then the rest following Aj are 0, right? And so we're actually just left with this sum Aj, Vj, okay? In fact, I have a friend named Vj, it's kind of funny. Okay, and so we divide by negative Aj on both sides, and we follow an analogous process. Since it's non-zero, it works. We add Vj on both sides, and in general, we can write Vj as some linear combination of the previous vectors, and so indeed, Vj is in the span of the previous vectors, Vj minus 1. All right, good. Proof of the second claim. So the span is unchanged when we remove Vj. Well, we can quickly see why that's the case, because, well, we've written Vj as a linear combination of the previous vectors, And so in general, if we take the entire linear combination, so, well, I'll write it out, v1 plus dot 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 plus aj vj plus dot 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 plus an vn, we can replace vj by this span, by this linear combination that we found for vj, just by dividing both sides by that and adding. We can replace it by that, and that will give us, that will allow us to change up some parentheses, move some of these coefficients, combine those with the previous vectors, the previous scaled vectors v1 through vj minus 1, and so we'll be left with a linear combination, but leaving out the vector vj. And so indeed, the spans are unchanged. So I haven't written everything out, but we can write this as sum b1, v1 plus dot 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 plus b j minus 1, vj minus 1 plus bj plus 1, vj plus 1 plus dot 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 plus an vn, bn vn. Okay. Using the previous result. Okay. So you can fill in the gaps there of what I've explained everything that I needed to explain, but if you want to be more rigorous, you can literally plug in our formula that we found for Vj, a linear combination of the others, and you'll actually find these coefficients exactly. But that's all that is sufficient for now. And so that's all we need for the linear dependence lemma. And now let's get to a crucial result, and that is that the length, so suppose, I can't write today, suppose v1 through vn is a linearly independent. I'll write inside of our vector field v is linearly independent. Okay. I again butchered the spelling. And W1 through Wm is a spanning list. Again, we defined spanning list last time. These vectors span V is a spanning list of V. Then the length of 1, we'll write this as 1, 2, is well, we could write it more efficiently, but it's less than or equal to 2. So proof, we want to show that n is less than or equal to m. Okay, so this is pretty intuitive, fairly intuitive if you think about it, but we need to see why this is the case more rigorously. Alright, so we're going to use a pretty interesting technique. We're going to start off by listing out the step 1. So it's like we're going to be going through an algorithm. Step 1, consider the following list of vectors. U1, we'll say V1, W1, all the way to Wn. this is a set of n plus 1 vectors, but it's linearly dependent because by assumption, these vectors span V. They span V, and so V1, since V1 is surely inside of V, V1 is a linear combination of these, and so by our proposition earlier, it's linearly dependent. And so we can use our linear dependence lemma. We can use our linear dependence lemma and note the following. We can remove one of these w's, right? Even though V1 is indeed a linear combination of those, there are no previous V1s. Because if now we use our special case that the span of the set with just 0 is the empty set. Well, the span, sorry, I got that mixed up. The span of the empty set is equal to, span of the empty set is equal to the set with just 0 in it. So the only way we could remove V1 using the linear dependence lemma is if this was 0, right? Because the span of the empty set, which is the only previous element there, is indeed 0. However, V1 through Vn is assumed to be linearly independent, and so it can't be 0. Otherwise, that would contradict the fact that it's linearly independent. All right. And so we can write that out. So since V1 0, V1 cannot remove V1 through the linear independence lemma LDL. We'll abbreviate it as LDL. Now, and then by the linear dependence lemma, I might be saying linear independence lemma accidentally, but you know what I mean. So by the linear dependence lemma, this is a dependent list, so there surely exists a vector here, which is not V by what we've shown here. There are no previous elements there. There surely exists a vector W here, such that we can remove it. Okay. And so, yeah, so we'll remove a W, okay? So that's so there exists a J in there such that remove WJ. Removed. Okay. And step 2, we again add another V. So step, I can't write. Step 2, we write V1, V2, and then W1, Wn, missing Wj. We don't have Wj. So every step we're adding and removing, consequently removing a vector. So we added a V2, and now we need to add a bit more concreteness to our example, to our method, because now behind V1, behind this vector V2, there is indeed an element. It's not the empty element. However, by definition, again, we use the fact that it's linearly independent, and so surely the span of V1, V2 is surely not in the span of V1, otherwise that would contradict this fact. And so again, there surely has to exist a W, another W there such that we can remove it. Remove W, I don't know, Wi. And then we can, sorry for my bad handwriting here. And then we can, also the marker is kind of running out, unfortunately. And then we continue this process. But notice that throughout this process, by the linear independence lemma, there surely has to exist a w that we can remove. So actually, we continue this process after n iterations. After n iterations, we need to have a wj removed after each of those iterations by the linear dependence lemma, because after all those iterations, that list, as we've shown, is still linearly dependent. And so, for this to be the case, after n iterations, note that we're going to have all of those v's accounted for. Therefore, this process terminates, this algorithm terminates. v1 through n will all be accounted for. And so, for there to be at least for each iteration, there has to be a vj accessible. Through after n iterations, there has been a wj accessible after each iteration. Okay, a lot of this is just words, and so there has to be at least as many wj's as vj's. QED. Oh man, we're running out. Okay. Because that tells us that then the length of w at 1 through wm, so that w1 through wm is at least as long as the list from v1 through vn. So we've shown that m is greater than or equal to n. Alright, nice. So that is an important result. Notice that actually shows that our standard basis, as we know, well, we can write, oh boy, running out, Fn, which is spanned by standard basis, E1 through, don't worry about this for now if you haven't heard of basis yet, by standard basis, this is a spanning list for Fn, right? And so there is no linearly independent set that exists as a subset of Fn, such that it's longer than n elements. All right. So that's important. And there goes my eraser. So we'll continue our discussion in the next episode. See you then.